Red dwarf. Look up at the night sky. Almost every star you need a telescope to see, the faint, easy-to-miss ones, is probably a red dwarf. They make up roughly 75% of every star in the universe, yet you'll almost never spot one with a naked eye. Small, cool, and dim, with surface temperatures around 2,500 to 3,500 Kelvin, most weigh in at just 8% to 50% the mass of our sun. But here's the wild part. Because they sip their hydrogen fuel instead of gulping it, red dwarfs can burn for over a trillion years. The universe itself is only 13.8 billion years old. Do the math. Not a single red dwarf that has ever existed has had enough time to die yet. Orange dwarf. If red dwarfs are the universe's slow burners, orange dwarfs are the sweet spot. Also called K-type stars, they sit right in the middle, bigger and hotter than red dwarfs, smaller and cooler than our sun, at 3,500 to 5,000 Kelvin and 60% to 80% solar mass. And that middle ground might make them the best real estate in the galaxy for life. They're calmer than red dwarfs, throw far fewer dangerous flares, and stick around for 15 to 30 billion years, 3 times longer than our own sun will last. That's an enormous head start for evolution to do its work. Yellow dwarf. Now for the star you already know, yours. Our sun is a yellow dwarf, a G-type star, ranging from 5,000 to 6,000 Kelvin. Here's a fact that surprises most people. Yellow dwarfs aren't actually yellow. Seen from space, they're white. The yellow you see from Earth is a trick of our own atmosphere, scattering shorter wavelengths of light before they reach your eyes. Yellow dwarfs live about 10 billion years, and our sun, at 4.6 billion years old, is basically middle-aged, right around the halfway mark. When it finally burns through its hydrogen, it won't just fade quietly. It will swell into a red giant, then shed its outer layers and collapse down into a white dwarf. White dwarf, which brings us to the corpse of star. A white dwarf isn't alive. It's what's left after a star has burned through everything it has. Picture something the size of Earth, but packed with the mass of the entire sun. The density is almost impossible to imagine. A single teaspoon of white dwarf material would weigh about 5.5 tons on Earth, heavier than an elephant in a spoon. No fusión happens anymore. It just radiates away its leftover heat, cooling for billions upon billions of years, on its way to becoming what's called a black dwarf. There's just one problem. The universe isn't old enough yet for a single one to exist. Blue dwarf. Which raises the question, what happens to red dwarfs, given how long they live? The answer is a star that has never once been observed, the blue dwarf. It's entirely theoretical, predicted, but never confirmed, because nothing in the universe is old enough yet to have become one. The idea is that as a red dwarf finally starts running low on hydrogen, it won't balloon into a red giant like bigger stars do. Instead, it will slowly heat up, climbing in brightness and shifting color from red to blue over unimaginable stretches of time. Brown dwarf. Somewhere between star and planet, there's an awkward in-between object, the brown dwarf. Think of it as a star that almost made it. It formed the same way stars do, but never gathered quite enough mass to ignite true hydrogen fusion. At 13 to 80 times the mass of Jupiter, it can fuse deuterium and sometimes lithium, but not hydrogen. So instead of shining steadily, it just slowly cools and dims. Surface temperatures range from 300 to 2,500 Kelvin. Some brown dwarfs are actually colder than certain planets. They're notoriously hard to spot because they emit so little light, but astronomers suspect they might be nearly as common as stars themselves, quietly hiding throughout the galaxy. Subdwarf. Not every star fits neatly into the main sequence. Subdwarfs are the underachievers, dimmer than a typical star of their type, mostly because they contain far fewer heavy elements. That thinner, less opaque outer layer makes them look bluer and fainter than expected. Subdwarfs tend to be ancient, often found drifting through the galactic halo, and their scarcity of heavy elements is basically a fingerprint of the early universe, proof they formed back when those elements simply hadn't been made yet. Blue giant. Now the scale flips completely. Blue giants are the universe's overachievers. Massive, blazing hot, with surface temperatures north of 10,000 Kelvin and luminosity tens of thousands of times brighter than our sun. But there's a catch to burning that bright. They burn out fast. While a red dwarf can coast for a trillion years, a blue giant tears through its fuel in a few million years. It's the stellar equivalent of a sprinter versus a marathon runner. Red giant. Every star's fuel runs out eventually, even ours. Once a star exhausts the hydrogen at its core, it starts fusing hydrogen in a shell around that core instead, and the outer layers respond by ballooning outward, sometimes to tens or even hundreds of times the star's original size. Despite growing enormous, red giants actually cool down, dropping to around 3,500 to 5,000 Kelvin, which gives them that deep red-orange glow. In about 5 billion years, our own sun will make this exact transformation, expanding so far it swallows Mercury and Venus whole, with Earth uncomfortably close to the edge. Blue supergiant. If a blue giant is a sprinter, a blue supergiant is a sprinter on fire. These are among the hottest, most luminous stars in existence, 10,000 to 50,000 Kelvin, shining hundreds of thousands of times brighter than the sun, and weighing in at 10 to 100 solar masses. They're what happens when the most massive blue giants finish burning hydrogen in their cores and start expanding into the next chapter of their lives. And that chapter rarely ends quietly. Most blue supergiants are destined for supernova. Red supergiant. If size alone decided the podium, red supergiants would win outright. They're the largest stars by volume anywhere in the known universe. So balloon out past 1,000 times the radius of our sun. Take Betelgeuse. If you dropped it into the center of our solar system in place of the sun, its surface would swallow Mercury, Venus, Earth, and Mars, and could reach all the way out to Jupiter. Despite that almost incomprehensible size, they're relatively cool, 3,000 to 4,000 Kelvin, but their sheer scale still makes them blindingly luminous. They're also living on borrowed time, unstable, aging fast, and almost certainly headed for supernova. Hypergiant. Beyond supergiant, there's one more tier. The biggest, brightest, rarest stars we know of, hypergiants. They can outshine the sun by millions of times and pack in over 100 solar masses. They're also spectacularly unstable, constantly shedding huge amounts of material through violent stellar winds, and they come in several flavors, blue, yellow, and red hypergiants. UY a red hypergiant, is one of the largest stars ever measured, with a radius roughly 1,700 times that of the sun. Like the other giants, they burn out fast, living only a few million years before nearly all of them end in a catastrophic supernova. Wolf-Rayet Star. Some stars don't just burn hot. They burn so violently they strip themselves bare. Wolf-Rayet stars have blasted away their own outer hydrogen layers, exposing the helium-fusing core underneath. Surface temperatures can top 30,000 Kelvin, and in extreme cases exceed 200,000 Kelvin, making them some of the hottest stars ever recorded. They fire off intense stellar winds, hurling material into space at up to 2,000 kilometers per second, sculpting glowing nebulae around themselves in the process. Wolf-Rayet stars represent one of the final chapters for very massive stars, and most are headed towards supernova, or something even more extreme, a hypernova. Neutron Star. When a truly massive star finally explodes as a supernova, what's left behind is almost beyond belief. A neutron star crams 1.4 to 2.1 times the mass of our entire sun into a sphere only about 20 kilometers across, roughly the size of a city. The density is so extreme that a single teaspoon of it would weigh about 6 billion tons. Inside, electrons and protons have been crushed together into neutrons, packed as tightly as physics allows. Some neutron stars spin hundreds of times every second, and standing on the surface of one, you'd feel gravity roughly 2 billion times stronger than on Earth. Pulsar. Now imagine that spinning neutron star firing beams of radiation out from its magnetic poles. And as it rotates, those beams sweep across space like a cosmic lighthouse. If Earth happens to sit in the path of that beam, we pick up a signal, a precise, regular pulse. That's a pulsar. Some spin so consistently that their pulses are more reliable than an atomic clock. When the first one was discovered in 1967 by Jocelyn Bell Burnell, the signal was so perfectly regular that scientists briefly wondered if they'd found something else entirely, an artificial signal from an alien civilization. They only half-jokingly nicknamed it LGM-1, Little Green Man. Magnetar. If a pulsar's magnetic field is impressive, a magnetar's is almost absurd, roughly 1,000 times stronger than a typical neutron star's, and up to a quadrillion times stronger than Earth's. Park a magnetar halfway between Earth and the Moon, and it would wipe every credit card on the planet clean. In 2004, a magnetar called SGR 1806-20 unleashed a flare so powerful that in just 1/10 of a second, it released more energy than our sun produces in 100,000 years, a burst strong enough to visibly disturb Earth's ionosphere from 50,000 light-years away. Black hole. Push a dying star's mass past a certain threshold, more than about 20 solar masses, and something even stranger happens. Gravity wins completely. Nothing, not even light, can escape past a boundary known as the event horizon, and what's left behind isn't technically a star anymore. It's a black hole. Stellar black holes typically run from about 5 to a few tens of solar masses, but supermassive black holes, lurking at the centers of galaxies, can weigh in at millions or even billions of solar masses. For most of history, black holes were purely theoretical, until 2019, when astronomers captured the first ever image of one at the heart of the galaxy M87, Quark star, and finally, the star that might not even exist. Quark stars are a hypothetical missing link between neutron stars and black holes. The theory goes that if the pressure inside a neutron star climbs high enough, the neutrons themselves could break apart into their raw building blocks, quarks, forming an entirely new state of matter. A quark star would be smaller and denser than neutron star, yet somehow avoid collapsing all the way into a black hole. In 2002, the Chandra X-ray Observatory spotted two objects that didn't fit either category, too small to be neutron stars, too large to be black holes. They remain unconfirmed to this day, the universe's most tantalizing loose end.